Bueno, profesora Liliane, tiene aproximadamente unos 45 minutos y luego pasaremos a una ronda de preguntas. Gracias.
Gracias, buenos dias, me ouvem bem? Sim? Buenos dias a todos, gracias a Alfredo por la introdução, e a Paulo pela invitação, e a Rómulo pela invitação. Eu vou falar em inglês, porque não hablo espanhol muito bem. Bueno, I'm going to talk about these semilinear parabolic equations with asymptotically linear growth. This is a joint work with Juliana Fernandes from University of Rio de Janeiro, and it's a recent work on this field of parabolic and elliptic equations. In fact, I work with elliptic equations and Juliana with parabolic equations. And we met some time ago and we started talking about some of very similar problems, and we started working on this problem, which translates to this work I'm presenting today. So I'm going to give an idea of the type of equations that we worked and the type of results we got. This is a very naive parabolic equations. We have the time term and the Laplacian of u, and a general nonlinearity f of u, which is going to be asymptotically linear in our case. The domain is bounded. We are working in a bounded domain, and the Dirichlet boundary conditions. At this moment, f is just a C1 function, and as we are going to see, we are going to assume conditions in f such that we have global existence in time, in forward time, for this problem. So we're going to have global existence of solutions in time, and then we're going to try to understand what are the initial U0 functions to give existence and bounded solutions in all time, and what are the U0 initial conditions that blow up in infinite time. So just the general theory in Henry and Pazzi cover our existence results. So we are interested in blow-up phenomena for these parabolic equations. If you have superlinear nonlinearities, which means that we have f of s equal to s to the p for p bigger than 1 and less than 2 star minus 1, which is the 2 star embedding, Sobolev embedding. So in a work that is very well known and is the reference for is a motivation for our work, which is by Gazzola and Wett, they study finite time and they describe finite time blow up. In our case, we are going to assume f of s asymptotically linear, which means that f of s is going to be something like a of s as s goes to infinity. So in this case, we are going to see just infinite time blow up. So the solutions grow up forever, but they don't blow up in finite time. This is a big difference between the two different nonlinearities, and I hope you're going to follow me on this for our discussion. So I'm going to give a historical background of this problem, just to see how it mixes elliptic and parabolic knowledge with respect to our approach. So existence of solution for the stationary problem is basically by critical point theory, mountain pass theorem by Ambrosetti-Rabinovitz, and Semigroup theory is applied when you have a nonlinearity, which is like just u to the p minus 1 times u. And also, there are many works which treat this parabolic problem with just a power type nonlinearity. For example, Tsuzumi, Oshino, Yamada, Payne, Sattinger, these are classical results by now. They really used some of the elliptic approach in order to face the parabolic problem. Cazenave, Lyons, also Lyons in Rn, Quittner, Souple, Gazola, and Wett. Gazola and Wett are our basic references. We follow pretty much some of their ideas in order to get results to our problem. Pacella, Yanni, Dick Stein, De Marquis. There are many people working nowadays, like in recent works, on this kind of parabolic problems. And also in Rn. In Rn, there has been important results recently by Yashivata, Ruf, Sani, Terraneu. Del Pino has solved some conjectures using constructions by Lyapunov-Schmidt together with parabolic equations. So it's a very active area of research, and the kind of tools we are using, these people are using too, in order to approach the parabolic problem. Okay, in our case, we are going to face an asymptotically linear nonlinearity, which is basically some linear part times a small order term in U, a general f of u of this type. This type of asymptotically linear nonlinearities give rise to what is called in parabolic equations slowly non-dissipative nonlinearities. This has been treated in R, functions of one variable in X. This has been treated by Juliana, my co-author, with different authors in these recent works. So when the problem is in R, it's pretty much studied, well studied. So these are parabolic equations with asymptotically linear growth and typical models of slowly non-dissipative equations. Our main goal is to treat the case of higher dimensions. Also for asymptotically linear, so slowly non-dissipative equations, and to analyze the long-term behavior of the solutions. If they blow up, when do they blow up? How do they grow? That's the idea of our approach. But basically, with Juliana, we started talking about this work because I have done very similar works for the elliptic equation in Rn for n bigger than 2, and Juliana has worked with the parabolic similar equations in R. So we said, what could change if Rn is bigger than n bigger than 2? So that's how we exchanged the first ideas. So repeating the parabolic problem is this for n bigger than 2. That's the interest. And asymptotically linear, and we are going to call the lim sup of f of u over u as b. So basically what we are saying here is that f of s is like b of s when s is close to plus infinity. So this is the asymptotically linear profile of the nonlinearity. The solutions are going to be u of xt, because it's an evolution problem. And we are going to work in the space of H01 function, Sobolev space. The main hypothesis for those who work with elliptic equations is going to be this hypothesis. This hypothesis gives a monotonicity for the elliptic problem, which helps in order to find solutions of the stationary problem as minimum constraint minimization. So we can find solutions for the elliptic problem by mountain pass theory, but also solutions using constraint minimization. And this is a hypothesis that used there in order to project the stationary problem in the what we call Nehari manifold. So, the model case, I always like to present some model from physics, which would be a motivation for this to study this kind of equations. This is the very physical motivation. This kind of nonlinearity appears in many papers in physics. We cite some of these works in our reference, in our paper. And these are basically models which describe, for example, a light beam crossing a saturable medium. So if the energy of the medium can always return to the process and there's no saturation, usually the problem is described by u to the power 3, for example, for physics. But in our case, with saturation, we end up with this term which represents saturation of the problem. So this is going to be the saturation term. Depending on the media that you are describing the problem in physics, you end up on this kind of model. So that's the motivation we had. If n is equal to 3, this is the model. The lim sup of f of s over s, this is f of s, f of u. So the lim sup of f of s over s is 1 over s, the saturation constant. So the limit of the nonlinearity is pretty much, it's like f of s could be something like, oh, f of u, né? Let me say, f of u would be something like 1 over s u, this straight line. This is the limit at infinity, which means that it is asymptotically linear at infinity. So this happens when u goes to infinity. So it's a saturation forcing term. It's not permitted to grow as powers forever. So this is the saturation effect described by the physics. And when s is equal to 0, you end up with the cubic nonlinearity, which is a power nonlinearity, which was well studied by Gasol and Wett. First of all, we have approached this using variational methods. So we have to establish the variational setting. The variational setting is going to be, we build, according to the problem, an associated functional to the problem, which is u of u, 1/2 of norm of u squared minus the integral of f, where f is the primitive of f, small f, the nonlinear term, and we take the derivatives of this associated functional, and the critical points of the stationary solutions are going to be the critical points associated to this functional. So this is the usual variational settings for these problems. Critical points of the functional are weak solutions of the stationary problem. So when we work the stationary problem, we are going to use variational methods. Existence of a solution for the stationary problem. So it goes back to Bartolo Benchi Fortunato in '83. This is a very famous paper for us in elliptic equations, because it was one of the first approaches to asymptotically linear problems using variational methods. So they proved the existence of non-trivial critical points U of I, hence solutions for the asymptotically linear elliptic problem in bounded domains. So this is the big reference for us when working in the elliptic situation. But then, in order to give our approach for the parabolic equations, we decided to find solutions not by the work of Bartolo Benchi Fortunato, but using what we call Nehari manifold approach. What is the Nehari manifold approach? The Nehari manifold approach is you look at all points which satisfy this I prime of u times u equal to 0. Why do you look at this set? Because all the solutions are in this set, because the solutions, they have to satisfy what is a weak solution of this problem. A weak solution of this problem are those u that satisfy this for all phi. So if they satisfy this for all phi, they're going to satisfy this for phi equal to u. So if you are looking for solutions of the elliptic equation, it's very natural to look on this set, which is going to have properties like a manifold and everything. So we are going to look for the solutions in this Nehari manifold that we call. And then, in order to look for solutions in this set, first we look, for example, at the infimum of this functional on this setting. If this is achieved, it would be, for example, the least energy solution for the elliptic problem. That's how we find the least energy solution for the elliptic problem. So the description of N, the Nehari manifold of set, is all the functions that are in this set are far away from 0, or at least outside the ball in the H01 space. This is one quality which helps us a lot with respect to initial data. N is a C2 manifold at H01, which helps a lot when you want, for example, to do the formations on this set N. And one important condition in order to use the approach we used is this one, that every time you take radial projections T of u, the function on radial projections, you find just one projection on N. And this is going to be the maximum. The u that projects on N is the maximum on that direction. Let me make a picture. What happens is this. If you take u not identically 0, and you take the radial projections of u for t, a real number, because of the condition that f of s over s is increasing, that we have, there is this hypothesis that f of s over s is increasing. Because of this hypothesis, the projection t of u is going to go up and down and find only one projection in N. So you have only one. In this case, I made a picture as u in N, but you have just one T0 u that projects on N. This is not usual. This happens only because we have this monotonicity condition in red. So we have in our approach, so we're going to use this projection on N. The geometry of N, of this set of candidates for stationary solutions. Usually when we have the problem for example, f of s is s to the p power bigger than 1, like a Gasol and wet, which we call superlinear, usually the Nehari set is homeomorphic to a ball. This happens for the Nehari set. It's homeomorphic to a ball. But in our case, this is not so. Not all functions project. But even though not all functions project, we are going to find, for example, this is like T of u. There is a projection. T of v, another projection. Even though not all functions project, the Nehari set is going to be enough for us. Only those that project are going to help us in finding weak solutions. So this is the drawing of a general situation, and this is the projection on the Nehari manifold. So this is the like tau 0 of u for some u that you are projecting. Okay. So in order to use this constraint in our approach for the parabolic equation, we define two sets, n plus. N plus are the j of u bigger than 0, and n minus the j of u less than 0. And of course, n is the j of u equal to 0. Equal to 0. Okay. The first lemma that we had to study in order to use for the parabolic equations is the following. Concerning n and n minus and n plus, it holds. The energy of the functions is always positive if u is in n plus. There exists some radius such that if you are in a ball of this radius, sigma, then immediately you get that u is in n plus. For any u in the Nehari set, in the Nehari manifold, this was taking the maximum of all those projections. So this is the maximum point. If you achieve the maximum, that's the u in n. And the most important result for us, which helps to study the parabolic equation, is the following. If you take any level k, I of k intersection n plus is bounded in H01 of omega. I of k are all the u such that the energies are below k. So if you have an energy below k, and if you are in n plus, you know that you're going to be in a bounded set of H01. So let's see. So remember, this is the most important step, I think, in the whole argument. We are always using this fact in order to get advantage to study the parabolic equation. Because this is such an important step in the paper, if you are interested, you can read the paper later. So I'm going to give an idea on why this thing works. First of all, we are in a bounded omega set. Since we are in a bounded omega set with the Laplacian, minus Laplacian, you have an spectral theory for this set. So consider, for example, B, which is a hypothesis for us. One of the hypotheses we have is that B, which is the limit of f of s over s, is like B, as s goes to infinity. The slope of the line which f asymptotes. So this B is bigger than the first eigenvalue, and it's a real number, so it's below some other eigenvalues, because the eigenvalues in a bounded domain like this for the Laplacian goes to infinity, plus infinity. So if you take u in n plus, then j of u is positive, because that's the definition of n plus. Then you arrive, because of this description of j, that the norm is above f of u times u. Consider U of n a sequence in with energy below k going to plus infinity. Okay, we are going to arrive in a contradiction because we want to prove that this sequence should be bounded. So if it goes to plus infinity, define V of n as U of n over the norm of U of n. So this one has norm 1. This one is bounded. Okay, since this is bounded, it weakly converges to some V. Because of the Sobolev embeddings that we have, this is going to converge strongly in LQ, okay? And it's going to converge almost everywhere in omega. So up to now is basically the information and the theory of Sobolev spaces. But then you have the nonlinearity, the primitive of the nonlinearity, F large, F capital, UN over N squared. This is going to be less than, because this is going to be less than B over B times the U squared, né? F of U is basically this if you're going to infinity. So we use this inequality and we exchange by B here because of this upper bound of asymptotically quadratic function for the primitive. But then, since we took B less than lambda J, this is going to be less or equal to 0. Okay, this is going to be less than equal to 0. You take the functional over this sequence, divide by the norm square. This is going to give this number plus this number, okay? But this is going to go, if you go to infinity, this is going to go, let me see here. This is going to go to a negative term, because that's what we just proved. So with negative sign, this is going to go to a positive term. This is the positive term. And we have this inequality. Because this is going to 0, taking the limit, this is going to go, because this is bounded. Because it's 1 on ik. Bounded divided by something that is going to plus infinity. So this goes to 0. Okay, this goes to 0. This term survives, goes to U, to V, because it's the norm L2. Okay, and in L2 you have compact embedding. And this is a positive term. But this is bigger than equal to 1/2 1 minus lambda J V squared, VL2 squared. Therefore, you have, take this term to the other side. You have that the norm is bigger than equal to 1 over 2 lambda J, which is positive. So you end up saying that V is not 0. Since V is not 0, it cannot be 0 overall in omega. So it has to have positive norm in some subset with positive measure. But then when you take the limit in a point of V of x, you are taking the limit of this term, but this term has something that is going to plus infinity. If this is going to plus infinity, then it's because the nominator has to go to plus infinity. So we end up seeing that UN, that sequence that we started, supposing that it's going norm to plus infinity, has to go pointwise to plus infinity in a subset of positive measure. Positive measure. But then, what's the problem with this? Take, by the assumption that we have that this thing is positive, take Fato's lemma on this subset omega 0, the lim inf of this thing is going to plus infinity, but then this is less than equal to the lim inf of this part, and the lim inf of this part is given by, this is exactly this term. But this term, since this is 0 because we were in the Nahari set, this is just I, or this is positive because we were in J positive, this is less than I of UN, which is bounded. So on one hand, this thing is bounded. On the other hand, this is going to plus infinity. This is a contradiction, therefore you have the assumption, the initial assumption, this was going to plus infinity is not possible. So this thing is bounded. So all this argument, I hope I gave an idea, but it's an elliptic argument, just Sobolev embeddings and the structure of the eigenfunctions and every eigenvalues. But anyway, every time you have a sequence which is in IK, energy below K, and N plus, then the UN is bounded. This is going to help study the parabolic equation. Let's see. So this is again the projection. Let me see. Okay. The idea is the following now. You take all the energies which are below D, where D was the infimo on the Nehari manifold or I of U. So this is the lowest energy possible. I'm putting this idea of the level curves, But D is the lowest energy that the functional I can have when restricted to the Nehari set. So D, here D is going to do is the number that we just used for the general K. So if you are below ID, you are below a level surface of level D, okay? So these are the level curves of the functional. If D is this level, the lowest level, so you're going to be, for example, for levels which are above D, you are going up on the Nehari manifold. And for levels below D, you don't intersect the Nehari manifold because the lowest level of the Nehari manifold is D. So on these levels which are below, you don't intersect the Nehari set. That's pretty much the geometry of the level sets. Okay. So let's see the existence and description of solutions of the parabolic problem. All of that I told you was the study of the elliptic problem. Now let's go to the parabolic problem. We write f of u as b of u, which is the asymptotically linear term, plus an error term. G is in C2 in our hypothesis. Under this hypothesis, we have this comparison with a power sum for the f of s. Because you have this comparison, you end up seeing that we were working on a parabolic problem with the forcing term Lipschitz continuous and bounded. Since it's Lipschitz continuous and bounded, the global well-posedness of our parabolic problem follows from standard elliptic or semi-group theory. So because of this bound in the nonlinearity, we have all the parabolic structure in our favor, okay? So existence for all time, forward time, is no problem for us because we have an asymptotically linear nonlinearity term. Therefore, we have a corresponding semigroup, which gives the evolution of the problem if we start with an initial data U0. So all the evolution in our problem comes from the semigroup theory of parabolic equations. Okay. Now, let's see, there is a factor that imposes a lot of information, gives a lot of information for our study from the spectral theory of this operator. So if you consider the sectorial operator minus Laplacian minus B where B is that constant of the f of s at infinity. The slope of f as you are far, far away from 0. So subtract this slope from minus Laplacian, you get self-adjoint operator. We have a theory of eigenfunctions for this because we are in a bounded domain. And these are the eigenfunctions and eigenvalues. We call them lambda tilde, and the lambda tilde are just the lambda eigenvalues for the Laplacian minus b. So since you are assuming that b is bigger than the first eigenvalue, at least one of these is negative. So in our problem, because of the assumptions that lambda 1 is less than b, we start with at least one negative eigenvalue. Okay? To prove that the solution semigroup cannot be dissipative, that is, there is no fixed absorbing set in the state space, okay? We use this, and a consequence of this is that the long time behavior of the solution cannot be analyzed through the description of compact global attractors. So this is a big difference with respect to other approaches, for example, the approach for u to the p minus 1 u. Okay, when you have a nonlinearity which is a power like this, you have some knowledge of global attractors. But since our nonlinearity is asymptotically linear, there is no compact global attractor for the problem. So we have to study the evolution of the problem in a different way. So for this purpose, we define GB, which is all the solutions that in time are uniformly bounded. So as the flow goes, as the problem evolves, the u of t does not blow up. This is the set GB. And the set G infinity for us is the grow-up solution. Since we don't have blow-up in finite time, what we have is grow-up solution in all time. So the solution just grows, and this is the situation in this case. Blow-up in infinite time for us is the L2 norm of the solution is going to grow forever. It's going to explode in infinite time. So these are the two sets that are describe the evolution of our parabolic equation. G of B, GB, can be defined as containing all the solutions converging forwards to a subset of stationary solutions. So the ones that start here are going to converge to a stationary solution. And G0 is the one that converges, that vanish in time. So these are the solutions that are going to disappear in time to 0. Okay? So those that die with time. Okay, the equation has the subset of bounded solutions. So what do we know about GB? G of B is not empty. Why? Because the problem, stationary problem, has a solution. There is a solution different from 0 for this problem, which was found using Bartolo, Benchi, Fortunato, for example, or the minimum of the Nehari manifold. So if there is a solution for the stationary problem, so this is going to be in GB. That's why GB is not empty. Okay? So at least one bounded solution, not trivial, we have. G infinity is not empty. This needs some reasoning, because it's not natural to see that there is one solution that grows forever. So what was the idea here? Take the eigenfunction, phi1 of the Laplacian, And then a multiple of this eigenfunction is going to have energy negative. So if you start with this kind of initial data, we know from this problem, the parabolic problem, we know that the energy decreases all the time because the energy in this problem, the derivative of the energy with respect to t is negative. So the energy is always decreasing as the problem evolves by the semigroup. So if you start with a negative energy, you are going to go down. And if you are down, you are not going to go, for example, to solutions, because solutions are either zero, stationary solutions, either zero, or they start from the energy of D, which is the minimum on Nehari. So it cannot go to GB, it cannot be in GB, so it has a norm that goes to plus infinity. So pretty much it's a constructive proof. We take the eigenfunction and using this as with a convenient C, very large C, we can prove that U0 is the initial data that goes to plus infinity, minus infinity, the energy. Okay, another important theorem which is was known for U to the P, but was not proved for the asymptotically linear problem is this. If you have an initial data in ID intersection n plus, then this initial data evolves to the zero stationary solution. And if you start in ID in n minus, then it evolves to something that blows up in infinite time. How do we see this? Take some function in I of D, which is the energy below this, and see how it evolves. Because I is decreasing, the energy is decreasing in time. So for some time later, or for after the beginning, for all times, this is going to be less than D. If it's less than D, it cannot go to a non-negative stationary solution. So the only possible approach is going to be zero or something that goes to plus infinity. That's the idea. Then, let me give a picture which is better. It's something like this. If you are with an initial data here, which is below D, D is this level set. If you are in an initial data which is below D, the energy is going to decrease. And it's going to decrease, and the only possible path or evolution for this initial data is going to be go to zero. That's the idea here. And on this side, if you are already below the least energy solution, and you are going to decrease, this thing is going to go to plus infinity. It has no way it can approach a stationary solution because all stationary solutions are above D. That's the idea. A remark here, if you start with G U0 in G0, some function that evolves to zero, then it's going to be in n plus inter ID after some time, okay? So it's going to, if it starts in G0, even though it can start very large, after some time it has to go to be below the level D of energy and has to enter in n plus. I'm not going to give the proof. It's better to show it in a picture. If you start in G infinity, at some time you have to go to n minus. You cannot decrease the energy and stay in n minus. Why? Because if you decrease the energy, you are going to enter in n plus, and then you're going to convert to some stationary solution. So if you are not converging to a stationary solution, you have to enter n minus for T large. I don't know if the idea. Another corollary that we get is that you have a neighborhood of the origin in H01, that all solutions that start in this neighborhood evolve to 0. So all solutions that start here evolve to 0. Then they cannot go to any other stationary solution, because the energy is decreasing, and then the stationary solution you have is 0. Other information that we get for the evolution of the problem. If you start with a function that changes sign, this changes sign, but each one of them is below the energy level D, each one of them is below the least energy D, then the evolution is to 0. We used many comparison principles and everything in order to prove this result. I'm not going to prove, just the idea of things that you can get from this approach with respect to the subsets of N, okay? Not the subsets of N, the subsets related to the Néraire manifold. Anyway, what we are doing here is taking some information from the elliptic problem in order to decide or to conclude about the parabolic problem. All these that I showed before were solutions close to D, the energy level D. So if you are looking at the functional I of u, so here you have H01, and here you have the energies. If we are looking here or below here, we know a lot how they evolve. But now comes the question, what about if the initial data has very high energy? Okay, so we have some results for high energy and grow up and the blow up solutions. For any high energy initial data, there exists one positive function that evolves to 0 and another positive with high energy that blows up in infinite time. So it's not a matter of energy. You can start with very high energy and evolve to 0 or evolve to plus infinity norm, okay? Of course, if you are evolving to a positive G infinity, at some point you have to cross to N minus, okay? Also, there exists omega n in N minus such that the energy is above this and it's also evolves to G infinity. So you can start in N plus and go to G infinity, you can start in N minus and go to infinity. So it's not really a matter of high energy. It should be something else to take you to plus infinity, blow up in infinite time, or to 0. So this is the picture of what I was talking. So you can start, for example, with very high energy. Here is high energy M, and U of M is going to evolve to 0. This is possible. And also you can start with very high energy in N plus and go to infinity. This is possible. Or you can start with high energy in N minus. N minus would be, okay, here is N plus, and here is N minus. You can start with high energy in N minus and also evolve to plus infinity. So it's not a matter of high energy that is going to decide if the thing stays bounded forever or if it blows up in infinite time. It's something else. So here was the, I don't know how to draw, but anyway, this is going to be in G infinity, even if it's in N minus, okay? Now there is one question. Is it true that U0 in N minus always go to infinity? So we have this picture, the Nehari manifold, and we saw that there was something in N minus that goes to infinity, that is in G infinity. There is something here that goes to 0 and plus, and there is something here that goes to G infinity too. But the question is, because you are in N minus, is it true that N minus is the complement, negative complement of the Nehari condition? The Nehari condition was J of U equals to 0. J of U is I prime U times U. Okay. The question or the intuition could lead us to think that if you start in N minus, if you start outside the Nehari set, then you are going to blow up in infinite time. Is it true? We proved that that's not true. And this is an interesting approach in this problem is start with the ground state solution. There is initial data very close to this ground state solution such that the initial data U0 is in N plus and goes to a stationary solution, not 0. And there is something in N minus that also goes to a stationary solution. So this tells us that it's not true that if you start in N minus, you go to G infinity. You are in G infinity. No. You can start in N minus and still approach, in this case, we found that they approach the stationary solution phi. Let me see if I can, I'm going to skip the proof. The proof is based in the eigenfunctions, eigenvalues, spectral theory, gives you the stable and unstable manifold, and then you find a direction that goes to the stationary solution. But let me see if I have, this is the proof. You work with the linearized operator around the stationary solution, and then we end up finding a stable direction that arrives in there. Let me just, I'm almost over time, but let me give you an idea on what's going on here. What's going on here is you have, for example, the Nehari manifold where the least energy solution is here, for example, this would be phi. And then you have something, let me see, something close to this solution. You have one that is in N minus and goes to this, and then you have one that is in N plus and goes to this. So it's not true that if you start with an in N minus, you always go to infinity. You are in G infinity. This is not true. We find one very close to the stationary solution that moves to the stationary solution in time, okay? And then finally, we could use the Nehari manifold in order to find what we call the perfect separation of sets, okay? If you have a function that projects on the Nehari manifold, so if you have one that projects in the Nehari manifold, T of U here. If you have one that projects in the Nehari manifold, and it's positive, you can follow the projection. Part of it is going to be in N plus, part of it is going to be in N minus, and part of it is going to go to GB or to G infinity. Just to conclude, what we prove here is the following. If you take T of U for a U that is projectable in the Nehari, so if it's projectable, it's something like this. Okay, here is the projection on the Nehari manifold, T of U. T0 of U belongs to Nehari. okay? What we found was there is an alpha star such that, so this is going to be the alpha star U. There is an alpha star U such that for all projections up to this point, if you start here, if you start U0 here, you are going to go to 0 or go to some stationary solution. And if you start on this side, you're going to go to be in G infinity. You're going to explode in infinite time. So it's a perfect separation we call for functions that are positive. So if you start at the positive set of functions, I'm almost finished, there is a perfect separation that are the initial data that go to 0, a stationary solution, and the other part goes to plus infinity. But this was possible only for positive functions initial data. We could not prove this for sign-changing solutions. Anyway, let me finish. This was proves that it's an open set. Just to finish, there are some open problems with respect to this approach is the perfect separation, which I just talked. Can you say something like this for a sign change in initial data? Because the perfect separation that we proved was for T of U, where U is a positive function. So there is a perfect separation, which is this side is in GB, and this part is in G infinity. Wherever you start, you're going to go to a stationary solution, or you're going to explode. But this was possible for U positive. Can you do the same? Can you have a perfect separation for initial data which change sign? We don't know. We are not able to prove. Another question is, if you start with any stationary solution of problem P, which is the elliptic problem, then there exists U0 of local stable manifold for phi in arbitrary close to phi, where points go to phi on one side and the other. This would be the same reasoning that I told you, but for other phis which are not the ground state. If you start with another stationary solution, can we find a neighborhood where things go here and go here from n minus and n plus? We were not able to prove because this requires a very deep study of the spectrum of the linearized problem, and we are not able. There are many questions, but these are some that I would like to highlight at this point. So, thanks for your attention, and nice to be here.
Muchas gracias, profesora Liliane, por su palestra. Si alguien tuviese alguna pregunta o comentario, podría escribirlo acá en el chat del Google Meet o también levantar la mano.
Creo que han levantado 2 personas la mano, Alfredo.
Bien, Gilmar Jarbugio tiene una pregunta para la profesora Liliane. A ver, Gilmar. Bien, y también Rómulo Díaz Carlos. Gilmar, a ver, lo dejo para que pueda hacer su pregunta a la profesora Liliane. parece que tendré algunos problemas. Rómulo, ¿estará ahí? Que desea preguntarle a la profesora Liliane.
Good afternoon, Liliane. I ask question in português?
Português, pode ser?
Pode ser. Liliane, em princípio, muito obrigado por sua extraordinária palestra. Na verdade, estamos muito gratos, todo o comitê organizador deste evento, do primeiro Congresso Internacional de Matemática Pura e Aplicada. Na verdade, muito boa sua palestra. Eu só gostaria de fazer uma pequena pergunta ali, né? Quando você fez um operador A menos Laplaciano mais um D por I, onde esse F de S sobre S se aproxima a esse B, e você construiu esses benditos autovalores que têm uma quantidade finita e depois, para um lambda chapeuzinho de n mais 1, vai para o infinito, né? Minha pergunta é, quando você, Nehari, você lo trabalhou em dois troços, em duas parcelas, né? A parte Nehari positivo e a parte de Nehari negativo. Então, essa é a parte de los lambda chapeuzinhos que vão de n mais 1 hasta o infinito. Isso está relacionado que quando vou trabalhar com a parte de Nehari positivo?
Não. Em cada, vamos dizer, autofunção, você tem um número finito de, vamos dizer, um espaço de autofunções finito, né, para cada autovalor desses, e você vai tentar usar essa descrição do espaço, a gente usa essa descrição do espaço com essas autofunções para entender a variedade estável e a variedade instável em torno de cada ponto estacionário. Ou seja, isso é uma informação, Nehari é outra informação, e você tem que colocar essas duas informações juntas. Isso não tem nenhum efeito sobre Nehari, em princípio. Vocês entendem o meu português, ou o que quer que eu fale? Ou seja, uma é a teoria espectral e as direções positivas e negativas em torno do problema linearizado. Então, quando você tiver uma função estacionária, uma solução estacionária do problema, a gente vai linearizar em torno dessa função e vai encontrar menos Laplaciano, menos F' de φ, tá certo? O operador linearizado, e usando o operador linearizado, você vai ter Nehari, vamos dizer que Nehari fosse isso, e aqui você tem a primeira solução estacionária. Lineariza aqui e veja se tem um comportamento, por exemplo. Linearizamos aqui e nós vimos que tinha funções, né? Poderíamos encontrar funções U0 que começa aqui e converge para cá, e outra uma V0 que começa aqui e converge para cá. Ou seja, flows to the stationary solution. But this was in n minus, this was in n plus, and the flow here depends only on the stable manifold in the linearized problem. So, to understand this, you need more than the Nehari manifold, you need the stable and unstable manifold around phi. Ok? Não sei se lhe respondi, Rómulo.
Sim, ficou claro. Só que eu pensei que, o sea, la descomposición de cada Nehari dependía de esos autovalores. La verdad, como usted dice, al final, como você fala, al final, son cosas independientes que van a ayudar a encontrar esa solución que você está procurando, ¿no? Tá. Então, essa era a minha pergunta. Novamente, muito obrigado, Liliane, por aceitar participar neste evento que a gente está fazendo, e essa era a minha pergunta. Obrigado.
Obrigado.
Tenemos una última pregunta de Jesús Alberto León. Acá le puedo leer. Dice si será posible aplicar esas mismas herramientas considerando f con un comportamiento exponencial o si ya ha sido estudiado con un problema cuando f es exponencial.
F exponential would be, okay, in order to have all the Sobolev embeddings and the compact embeddings and the theory of Sobolev spaces, we have to be below the critical exponent. So we have powers for p less than 2 star, which is the critical exponent for the Sobolev embeddings, compact embeddings. So here we are working like this. If you are working in R2, the 2 star is plus infinity. And the natural growth here is exponential. Okay? So, exponential of u, alpha u, exponential of alpha u, for example. So I think that in R2, all this approach would be with the exponential growth, but not in Rn bigger than equal to 3, because for bigger than equal to 3, you have the bound for the compact embeddings. But in R2, yes, I think this approach could be done with exponential growth.
Okay. Muchas gracias, profesora Liliane, de parte de la Universidad Nacional del Callao y nuestra facultad. Le agradecemos enormemente por su participación y me gustaría mucho despedirlas con unas fuertes palmas también.
Gracias a todos.
Bien, a continuación, continuando con nuestra programación.